Welcome to this web lecture on distance metrics in transport. For transport companies, it's extremely important to know how far 2 points are apart. Because of course, if I want to optimize a route, if I want to optimize a distribution plan or anything, I of course need to know how far any 2 points in my system are apart, because if I don't have this parameter, it's going to be extremely difficult to find anything that resembles the shortest path. And we have multiple different ways how we can measure this distance. And the first one that we're going to look into is the case of a taxi operating in New York. So if we're sitting in a taxi in New York, this taxi will roughly follow a zigzag pattern. And the reason behind that is that New York's street layout more or less follows a grid pattern. And if we know that our underlying street network is give or take a grid network, then we can approximate the distance between two locations 1 and 2 by, first of all, the distance in the x direction and then the distance in y direction and just the sum of those two. The important part is that we have to take the absolute value because, of course, it doesn't matter if I go in this direction or in this direction. The distance between these two locations is always the same. The next thing that we can consider is the Euclidean distance. And the Euclidean distance is literally how the crow flies. So if we have a crow which flies around its nest, this crow would not fly like this. This crow would just fly like this. And that is quite simply because it doesn't have any sort of resistance in the air. It can just fly on the shortest direct connection. And that is what we refer to as the Euclidean distance, and this is the way that we compute it. So similar to anything that you learned in high school to compute the direct distance between two locations, we just use the distance in the x direction to the power of 2 plus the distance in the y direction to the power of 2, and then we take the square root. We can, of course, use these distances in applications. So, for example, here we have 5 locations, and we would like to know the distance, both according to the Euclidean and according to the Manhattan distance. So let's first look into the distance according to the Manhattan distance. So let's just say we're starting with the distance from the point 1 to the point 1. Then we have 2 minus 2, which is 0, plus 10 minus 10, which is also 0, and we get a distance of 0. That is also fairly obvious, because if I'm standing here and I would like to have the distance to myself, the distance is 0, and it should be 0 regardless of which kind of distance metric I am considering. But now let's say we're looking at the distance from 1 to 2. So from 210 to 10:8, and we would like to know the distance according to the Manhattan distance. So what we have to do is we have to go for 2 minus 10, which is minus 8. We then take the absolute value, which gives us plus 8, and to that we add the difference between 10 and 8, which is 2. So we get a total distance of 10. So now let's look into the other direction. So and for that we use the Euclidean distance. So now we go from 2 to 1 and we use the Euclidean distance. Then the first thing that we have to consider is 10 minus 2, which is 8. Which we then take to the power of 2, so we get 64. Then we take 8 minus 10, which is minus 2. We take this to the power of 2, which gives us 4. Then we add these two numbers, we get 68. And then we take the square root of that. And the square root of 68 is roughly 8.25. What I would like you to do is just fill out this table and look at all the other distances, both using Manhattan and using the Euclidean distances. Of course, this is not the only distances or distance metrics that we can consider. So, for example, if we look at ocean freighters, be it ocean freighters that actually transport freight or the Titanic, they do not go on what we think is the shortest route on a map. So to look at that, you can just compare what the shortest route is between Southampton and New York, so the route of the Titanic. And if you do that on a map somewhere, then you would think that it would go very far south. But if you then look at where the Titanic sunk, that is in the Arctic, then you're going to be confused if you look into a map. But if you then look onto a globe, you're going to see that actually the shortest connection between Southampton and New York goes considerably further north. And this shortest route on the globe is what we refer to as a great circle distance, and this is how we compute it. Airlines in parts also use great circle distances. So for example, if we have a plane that goes from Los Angeles to Tokyo, they follow the great circle distance if they go from America to Asia. But when the flight goes back, they go considerably further south. And the reason behind that is that an airline does not necessarily look for the shortest route, but they're looking for the cheapest route or the fastest route. And the fastest route in this case is if you just use the wind that is anyways in very high distances in our atmosphere, and just let yourself being carried with this wind. And this is what we refer to as a jet stream. And this is, for example, the route that an airline would choose. They would not follow the great circle, but they would follow the wind. Also, we wouldn't usually use any of a standard metrics, so Manhattan or Euclidean, if we're in European cities. European cities don't have this American grid network, but are usually very historically grown. So, for example, if we're just plotting it into Google Maps, we would like to go from the city center in Eindhoven just to the University of Eindhoven. That, if you walk, is maybe 20 minutes, but if you drive, it's also going to take you 20 minutes because you have to go around. So here we have 3 possible routes. One of them is going zigzag over here. Another one is first going relatively far to the south and then going around. And the other one is first going west, even though you actually have to go east. So all of these 3 routes are taking massive detours, and that is because these routes are the only thing that is permissible using the street network and the permissible speeds, etc. So we have a lot of different kind of distance metrics depending on what kind of application we're having. What I would like you to take away from this web lecture on distance metrics is the Manhattan distance, the Euclidean distance, and the great circle distance, as well as, of course, some other distance metrics and why we sometimes go away from those standard distance metrics. And what I would like you to do as a preparation is looking into calculating these distances using the Euclidean and the Manhattan distance. Thank you very much.